And this is Alex Anderson here with another geometry video. Okay, so you know what that is, props to you. Anyway, so I love geometry and I'm making these videos about cool geometry theorems that I like, and I think I'll start putting together a more full course curriculum on kind of intermediate level math competition geometry because I have some experience teaching that. Alright, so I'm going to talk about a theorem that I find to be pretty fantastic. Okay, so what are we talking about here? So let's suppose we have a triangle ABC. So let me draw this triangle here, and then I'll label the vertices A, B, and C. Let me fix that there, make my triangle oblong. Alright, so given 3 points, we can form certain symmetric combinations of those points, and so let's consider the following. Start with segment BC and take the midpoint, and then connect that midpoint with the opposite side, or the midpoint of BC with the opposite vertex A. So this line here is called the median that goes from A to BC. Alright, and then similarly we can take 2 more midpoints of the opposite sides and connect the midpoints of the sides corresponding vertices. Alright, so when we do that process of taking midpoints of the sides and connecting those midpoints to the opposite vertices of the triangle, we have 3 segments that happen to pass through a point. So this is a very cool thing that I think doesn't get a lot of credit. So let me call this point G. G is called the centroid of triangle ABC. So for the purposes of this video, I'm going to assume that these 3 lines are collinear, or these 3 lines are concurrent, and that furthermore, the ratio of the segment AG to the length of segment, let me just label this, MG is 2 to 1. So AG to MG is 2. Alright, so this point's the centroid, and there are ways to form other ways to combine the 3 vertices into a point. So the next one we'll consider is called the orthocenter. So the way we form the orthocenter is we take lines that are perpendicular to the sides of the triangle through the opposite vertex, and these 3 lines also all pass through points. So taking a line perpendicular to AB through C, through BC, perpendicular to BC through A, we can see that these 3 lines are always concurrent at a point. Let me label that as H. And I will hide some lines because this is kind of a complicated diagram at the moment. Okay, so that's the orthocenter H and the centroid G. So the third sort of simple triangle center that we can think of is the perpendicular bisectors of the sides of the triangle ABC are all also concurrent to the point. So you take the perpendicular bisectors of the 3 sides of the triangle. We additionally see that these 3 lines are concurrent at a point. Let me call it O, that is the common notation for this point, and this is called the circumcenter. So in particular, the circumcenter is equidistant from all the vertices of the triangle, and there's a circle centered at O that passes through the vertices of the triangle. Alright, so one of the very shocking things is that this point, these 3 points all happen to lie on the line. So this is very remarkable in my opinion, and similarly doesn't get very much credit. So what I'm saying is you take any arbitrary triangle and you do these 3 constructions to get the centroid, orthocenter, and circumcenter. and they always lie in the line no matter what. So I think this is a really cool situation, and it's quite surprising. If you do a lot of geometry, it's hard to appreciate this, but I think it's really cool. Alright, so anyway, I've sort of selectively hidden lines that make the diagram complicated. Alright, so now our goal is to prove that these 3 points, H, G, and O, are collinear. So how do I go about that? So the first thing that I mentioned before is if you have the centroid G, then the length AG to GM is 2 to 1. So this can be proven relatively easily, and we notice that that property, we only need to consider a diagram of the centroid to prove that property. So you can prove that separately on your own. Similarly, the other thing we can observe is that OM and AH can also be calculated in terms of the sides and angles of triangle ABC, and also these calculations are done independently of each other. That is to say, we can draw a triangle with just triangle ABC, the circumcenter, and we can calculate this length OM, and we don't have to worry about points G and H. And similarly, we can draw a triangle ABC with point H and ignore points G and O. So one strategy that's very useful in geometry problems is you try and break down the complexity of a problem into manageable parts. Alright, anyways, so let us consider a triangle ABC again. So we have triangle ABC, and we draw the perpendicular bisectors, and those intersect at a point that is called O. Let me call that O, and then we have triangle ABC, move that over there, and let me just draw the last perpendicular bisector, and this is M. So let's calculate the length of segment OM. Alright, so the thing to notice here is that O is the circumcenter of triangle ABC, so that means that angle BOC is double angle BAC. So this is a common angle arc theorem that you should be familiar with. In particular, if you have an inscribed angle BAC, then the angle BAC is half of the arc BC, but arc BC just means angle BOC. And so now we have a little isosceles triangle here, BO is equal to OC, so that means these two angles BOM and COM are equal, and they're both equal to the measure of angle A. So in sort of geometric terms, these two angles are equal. Okay, so in particular, that means the length of segment OM is equal to the circumradius of triangle ABC times the cosine of this angle, which is angle A. So OM equals circumradius times cosine of angle A. Alright, so that's relatively straightforward. Now we can do a similar calculation with the orthocenter to find the other proportionality that we want. So let me just draw another triangle again, pretty quick, pretty easy. Label the vertices. Alright, now let's draw some perpendicular lines. This gives us the orthocenter. So orthocenter H. Okay, and then we're interested in AH. Okay, so similarly we can calculate the length of segment AH, and we will use some similar arguments. So let me label the feet of the perpendiculars of these two altitudes. So the altitude from B to segment AC intersects AC at E, and the altitude through C intersects AB at F. Okay, so now let us calculate the length of AF. So we just use some sort of standard manipulations here. So, alright, angle. Okay, so we want to get AH, right? So how can we write that? First, let's get angle BA. Label this point as D. Let's find angle BAD. Alright, so BAD is 90 minus angle B. Okay, so this here is 90 minus angle B, and this angle here is B. So let's consider that. So these two angles here are equal. Alright, next angle. So this angle gives us that AF divided by AH is equal to sine of angle B. So that means that we can rearrange that expression to get that AH is AF divided by sine of angle B. Similarly, AF is equal to this length AC, which is B, times the cosine of angle A. So that means AF equals cosine of angle A. Now if you write that out and manipulate it slightly, you get that AH is 2 times the circumradius of triangle ABC times the cosine of angle A, and this last step follows from the extended law of sines. Alright, so let's go back to our original diagram. So what we just explained is that AH is 2 circumradius times cosine angle A, and OM is the circumradius triangle ABC times cosine A. In other words, AH is double the length of OM. And similarly, we know that AG is double the length of GM. So if you're familiar with similar triangles, you might think that we have similar triangles on our hands, and you would be correct. So let me just highlight these two triangles. So there's one more observation that we need to finish the problem. In particular, consider lines AH and OM. We know that AH and OM are both perpendicular to line BC. Therefore, AH and OM are parallel lines. And in particular, because AGM is just one line, and we use equal inscribed angles to get that angle H, AG is equal to angle OMG. So these two small angles here and here are equal. So using SAS similarity, triangles HAG and OMG are similar triangles, which means that we have two equal corresponding angles, OGM and HGA. So we have two equal angles here and here, and so since AGM is a line, it follows that angle OGH is equal to 180 degrees. Therefore, OG and H are collinear. So that is the proof of the Euler line, and I think it is quite cool. So let me just give you a bit of insight into another proof of this problem, but I will be citing some facts that you may not quite know, but I'm just going to give you sort of a visual understanding of these facts. So let me just label the midpoints. So this midpoint is M, this midpoint is N, and then let me call this midpoint P. Okay, so when you draw the triangle that is formed by the midpoints of the sides of the triangle, that's called the medial triangle of ABC. In other words, M and P. is the medial triangle of triangle ABC. Alright, so the sort of general idea is we consider a transformation that shrinks A through G to M and correspondingly the other vertices. So in particular, let us do the following. So let me draw these lines here, and I'm going to help us understand this problem. Okay, so choose a point here, and then I'll draw some parallel lines as such. Alright, so this is going to be a kind of confusing diagram, so let me just hide some of the lines. Alright, so let us look at this, and let me also hide these two. Okay, so we take triangle ABC and we consider a shrinking that shrinks this triangle through point G and then goes all the way through and continues back out again to get triangle MNP. So again, you see here triangle ABC gets mapped to triangle MNP under this transformation. So in particular, this transformation is called a homothency. And you would say that a homothency centered at point G with ratio -1/2 takes triangle ABC to triangle MNP. So the reason for the -1/2 is because this length AG gets mapped to half its length, which is MG, and also A and M are on the opposite sides of point G, so there's a minus sign. Okay, so we have this transformation that maps the triangle ABC to triangle MNP. So as you notice, when I transform point B, it always, so where my cursor is the sort of trajectory that B goes along when I transform this. You notice that this point always lies on the line BG. So, and similarly, let's talk about transforming the orthocenter. So let me just quickly draw the orthocenter of this triangle. So again, it's getting kind of messy. Call this H prime. Okay, so this homothency transforms the orthocenter H prime to some new points. So you can see the orthocenter tracks along with the triangle, and so this diagram is quite suggestive. We see that sort of by construction, it seems very likely that this point H prime is actually the same as point O. So let's actually prove it. Okay, so H prime is the orthocenter of triangle MNP. So it's pretty easy to show that H prime is the circumcenter of triangle ABC, which is O, and we can use the following arguments to explain why. So H prime is the orthocenter of MNP, so that means H prime lies on this line here, which is the line through M that's perpendicular to NP. However, we notice that NP and BC are parallel. Therefore, as this line here is perpendicular to NP, it's similarly perpendicular to BC. That means that H prime lies on the line through M that's perpendicular to BC. By symmetrical arguments, we know that H prime also lies on the line through N that is perpendicular to segment AC. And so that means that H prime lies on the perpendicular bisectors of triangle ABC. However, three lines can only intersect at one point. So H prime must be the intersection of the perpendicular bisectors of triangle ABC, which is the circumcenter O. Thus, H prime and O are the same point. Okay, so, and then it follows that HG and O are collinear. Alright, so that is the other proof, and the argument using homotopy is a bit more advanced, and you need to know some properties of homotopy, but I think it is quite a cool proof, and I am looking forward to doing more videos and also optimizing how I do these videos. In particular, I think it'll be a good idea in the future to have some way of writing out the statements. I think that'd be much more useful, make it more like a traditional lecture. And just in general, I'm very excited about the idea of online learning, and I think there's a lot of potential to be really transformative in education. In particular, me as someone who really likes geometry is able to make these videos to communicate geometry to other people, and I hope to produce really good educational materials that other people can use. I've always been a big fan of Euclidean geometry, and I always love sharing my enthusiasm for it. So I hope you guys enjoyed this video, and I'll see you guys next time.